Hey, CP Math 1, this is Mr. Roberts at Shasta High School, and I'm going to go over the Chapter 3 practice test so you can see not only answers, correct answers, solutions, but also some techniques. Remember, learning happens in your mind. So as you're thinking about these things, right, kind of talk to yourself and say, do I understand what's being said here? How could I use this? How could I practice this? Um, Make sure that you understand and that you're not just an observer. So the first question, right, involves some functions, and the functions here are using the y equals notation, but in the first two cases, we are given the inputs. I know that we're given the inputs because it says right up here that, hey, here's an input of 3, here's an input of, or -3, here's an input of 2. And the question is, for these, what is the output, right? What results when you give these functions either 2 or -3? Below the question flips and it says, hey, the output is given, right? The output is 23, the output is 8. The question here is, what is the value of x that will make these values come out of the function? So let's go ahead and begin here. We'll take a look at the first one. It says, hey, here's a function. The definition of this function is that you take an x, you cube it, that is, raise it to the third power, and then you add to that 3 times that input. So whenever I'm evaluating a function, I like to use a set of parentheses to hold the value that's going to be placed into the function. So this space that I've just created right here is going to be used to get the value of 2. So you can see I've just modeled the first part of it, x to the third. So I've got something to the third. And then I'm going to go ahead and include plus 3 times the value of, and there's an x. And again, x is going to go in both of those spots. So in both locations, we're going to write that x is the number 2. And then I'm just going to evaluate these using orders of operation. The first thing I'll evaluate here is this cubing. So this is 2 raised to the third power. 2 to the third power is the number 8. That's 2 times 2 times 2. And then to that, I'm going to add the result of 3 times 2, which is the number 6. 3 times 2 is 6. So I get a value of 14. One thing that you can always do is use your calculator to assist greatly in evaluating functions and checking answers also. So in this case, if I wanted to, I could come in with the classroom calculators and I could say, look, I want to go ahead and tell my calculator what value of x I want it to use. So I can just say, hey, here's the number 2, and I would like for you to store that in the variable x. So 2 is going to go into x. And when I press enter, my calculator confirms, okay, x is 2. And I can see that's true because anytime I press x now and press enter, it'll say, yeah, I got the number 2 here. What that lets me do is type the expression exactly as it appears on the screen. So I can say, hey, I want to know what x, and I want to go raise to the power of 3. And to that, I want to add 3 times that value of x again. And when I do that, you can see I get exactly the number we got on screen. We get the number 14. All right, let's continue with the second part, part B. On this one, we are now given a value of -3. So same exact deal. I'm going to go ahead and look at the definition of this function. I can see what it is here. It's 2 times x is going to get squared minus 4 times the input value of x and then plus 6. So I'm just going to go ahead and write 2 times, here's a space for my x where I'm going to square it, minus 4 times, here's a space for my x, and then plus the number 6. So you can see here I've got this location where I'm going to be placing my value of x. This time my x is the number -3, so I'm going to carefully place that in here. Here's my -3, and here's my -3. So as I take a look at this, right, I'm going to have to go ahead and square that -3 first. And when I square -3, that is a -3 times an additional -3, so it produces a value of 9. So this is going to become 2 times the number 9. And then I'm going to have minus 4 times -3, which is actually going to be a plus 12. And then finally, I'm going to add the number 6 to that. So as I look at it, I can see the long line of values here that I have to evaluate. It's going to be 2 times 9 plus 12 plus 6. 2 times 9 is the number 18 plus 12 and then plus the number 6. So as I evaluate that, a function, right, 18 plus 12 is 30, and then 30 plus 6 is going to be 36. So there's a few errors that could be made here. One of the most prominent one is not understanding the difference between the opposite of 3 squared and negative 3 squared. So for example, on my calculator, if I just come in and I just type the following, I'm just going to type, let me get this over a little bit here so we can see it. If I just typed on the calculator, what is the opposite of 3 squared? You can see it says that's the number negative 9. I know that's not true because when I square, well, that is true. That is the opposite of 3 squared. It's not what I'm doing here, though, because I'm being asked to square x, and x is the number negative 3. So if I want to show that I'm squaring negative 3, what I have to do is I have to say, hey, here is negative 3, and I need to square that. So when I square negative 3, I'm thinking negative 3 times negative 3, which gives me the value of positive 9. So there's a key difference there. Make sure you understand the difference between the two. Moreover, the other thing I could do is I could come along here and I could say, hey, negative 3 is going to be stored as x, boom. And then I can go ahead and type this expression, which is 2x to the second power, nope, not plus, sorry, minus 4 times x, and then plus the number 6. And when I evaluate that, you can see it gives me 36. Okay, let's continue. So now we flip the script. Instead of finding the output given the input, the question is, what input will produce an output of positive 23? And what I like to do is just say, hey, I'm going to write down the definition of the function. This function is defined as take 2/3 of x and add 7. And I'm going to set the definition of this function equal to the output that I want, which is 23. So when I do this, I get a very nice looking equation that's going to allow me to solve for x. The first thing I'm going to do is go ahead and subtract 7 from both sides. And when I take 23 and I subtract 7, I believe I get the number 16. So this equation becomes 2/3 times x is 16. And the next thing I'm going to do is I'm going to use that thing we've talked about this chapter, fraction busters. I'm going to get rid of this fraction. You can see here's a denominator of 3. I want it to go away. So I'm going to multiply both sides by 3. If I take the number 2/3 and I multiply it by 3, and I want to demonstrate this because I think some of us don't see this. Here's the number 2/3. And if I take that number 2/3 and I multiply it by that denominator, right, 2/3 times 3, I just get the numerator, right? That's going to happen every single time. So when I look at 2/3 x times 3, that's just going to become 2x. And when I look at 16 times 3, that's just going to be 48. And then my last step here is I'm going to divide both sides by 2. When I divide both sides by 2, this side is going to become x, and this side is going to become the number 24. So x is 24, and it's definitely worth taking a moment and confirming, right? If I place 24 in for x, is 2/3 times the number 24 plus 7 more the output that I want, right? Is that the output I want? And without storing the x, I'm just going to say, okay, let's just look at 2/3. 2/3 times the value of x times the number 24, and then plus 7 more. Is that the number we want? Yeah, it's exactly the number we want. So with great confidence, I could say x is the number 24. Next problem, very similar, except this does involve the square root. So again, I'm going to follow the same pattern. I'm being asked to find the input. I'm asked to find the x value that will produce an output of 8. I'm going to take the definition of this function, and I'm going to set it to the desired output, and the desired output is 8. So this is one of those settings where we can use the idea of looking inside to find a value of x. So if I take a look at this expression, right, the entire thing inside here is this 1/2 x plus the number 3. I'm sorry, 1/2 times x plus 31. That box, right, that box has to be a specific number if its square root is the number 8. And the number it actually has to be is 64. So I know, right, from just number sense and experience that the square root of 64 produces an answer of 8. So I know looking inside that thing inside the radical has to be the number 64. Well, that's a great story. How do I deal with that? Well, you just make it 64. We're going to make it 64 by saying, look, 1/2 times x plus 31 more must be the number 64 if the square root of it is going to be the number 8. So I just set it equal to 64, and then I solve. First step is going to take the 64 and subtract. I'm subtracting 31 from both sides. So the left-hand side is going to become 1/2 times x is equal to the number 33. And the last thing I'm going to do is I'm going to fraction bust again. I'm going to multiply by 2 to get the fraction to go away. And when I multiply both sides by 2, the left-hand side just becomes x, right? 1/2 times 2 is 1x, and then 33 times 2 is 66. So the input that should create this output is 66. Before I move on, I'm going to check that on my calculator. So I'm going to go ahead and grab the square root template second, and then I'm going to come down here to squaring. You can see right above it's the square root. Inside of here, I'm going to look at 1/2. I'm going to multiply 1/2 times the number 66. Oops, I should probably put times 66. And then I'm going to add to that an additional 31. And when I do it, I get exactly the number 8. That thing inside became 64, and then the square root of it gave me 8. So x is, without a doubt, the number 66. All right, let's move on. Next, we have some monomials, just 2 of them here. And we're asked to simplify these things, rewrite them so that there's no exponentiation, right? First thing I'm going to do is this number, or part A. If I look at it, I can see something's getting squared, right? Something, namely everything inside of there, is being raised to the second power. So to raise something to the second power means I have to write down 2 of those. So I'm just going to go ahead and simply write, hey, I'm going to have an xy squared times another xy squared. The only thing that's getting squared here is the y's, right? And when I wrote that down, xy squared, xy squared. Now, if I look at that, I can see that there are 2 factors of x, right? There's an x times another x, which is x squared. And then in terms of my factors of y, there are 2 factors of y here. That's yy, and then yy, which is y to the 4th power. So far, this is what I've got. The next part, you can see that this is not being raised to a power, right? So the assumed power is just 1. Because it's not being raised to a higher power, I can just go ahead and write down, oh, this is the number 2 times an x squared times a y to the 7th. So the only number that's going to make it in my final answer is this one, right? There's the number 2. That's the only number that's here. Everything else is either x's or y's. And there's a certain number of x's or y's, but the only number that's part of my monomial is 2. So I'm just going to go ahead and write that 2 out front. And then in terms of x's, you can see I've got 2 of them here and 2 of them here. So I have a total of 4 factors of x in my answer. So I'll write x to the 4th power. And then in terms of y's, you can see that I have 4 of them here, 1, 2, 3, 4. And I've got 1, 2, 3, 4, 5, 6, 7 factors of y there. So 7, 8, 9, 10, 11. So there are a total of 11 factors of y in my answer. So this is y to the 11th power. So my final answer I'm going to write down is just 2x to the 4th, y to the 11th. This is the simplified version of our original problem. Now, fun fact, you should always be able to check or at least verify that it's plausible that this answer is correct. And one of the things you can do to test and see if you have a plausible answer is to do this little trick. I'm just going to say, for example, let's consider, maybe I'm going to say x is the number 3.2. Now, just that's completely arbitrary. I don't know anything about this. This is not an equation. I can't find a value of x. This thing doesn't equal anything. But I'm just saying, if x was 3.2 and y was, I'll say, 7.1, something should be true. This original problem and my my answer, my simplified version of this, my rewrite of this, my making that look simpler, should produce the exact same value as an output. So I can easily check that with my calculator by just storing those two values. So I'm going to say, hey, here's 3.2, and I'm going to store that as x. And then I'm going to take the number 7.1, and I'm going to store that as y. And you can see when you hit this button multiple times, it gives you different variables. So it gave me x, and the next would be y, z, t, a, b, c. I'm just using y, and I go boom. So now I've stored these two values, and I'm going to type in my original, the problem I was given, which was open parentheses, x, and then times a y raised to the second power. I'm going to close the parentheses and raise that to the second power. I'm then going to multiply that by open paren 2x to the second, and then y, boom, boom, raised to the seventh power. And I'm going to close those. I got to close the parentheses, right? No, go back, delete there, and close the parentheses. So when I look at that expression, you can see it's a huge number because it's 4.8 times 10 to the 11th power. So that decimal is moved 11 places this way. Now let's compare that with our much more simplified expression, which is just 2x to the fourth power, right? And then we have y to the seventh power. And you can see, oh no, this is y to the 11th power. And as soon as I type that, you can see, yeah, that's the exact same number, right? Now, this is not proof that we're correct, but it's confirmation that it's at least highly probable, very plausible that we're understanding things and we got these parts correct. So my original expression and the simplified one are producing the same output for any arbitrary values of x and y that I picked. Now, arbitrary x and y values to avoid, don't use the number 1 or the number 2 or the number 0, right? Pick some nice kind of funky decimal, because it's possible if your expressions are simple enough, you can have the wrong answer and still just happens by happenstance, you're getting the same outputs. All right, let's move over to the next one. The next one has this 24 over 8, and there's a numerator with a 24 on the top and an 8 on the bottom. So if I look at 24 on the top and an 8 on the bottom, that goes in evenly, and it's just the number 3, right? So 24/8 is the number 3. So the first thing I'm going to do is I'm just going to write this becomes 3 times x to the fourth power over x squared y to the negative second. Now, if I take a look at this, my numerator has 4 factors of x. So just visually, I'm going to say, hey, just in terms of x, I've got 1, 2, 3, 4 factors of x. And my denominator has 2 factors of x. So if I look at this, right, I've got 4 factors of x over 2 factors of x. I can see that 2 of these, right, will cancel out. These are gone. And what I'm left with is 2 factors of x up in the numerator. So for my next thing I'm going to write down in my process of simplifying this is going to be the same as 3x squared over y to the negative second. And then finally, we know that when we simplify monomials, we do not want to leave negative exponents anywhere. So the last thing I'm going to do is deal with this negative exponent. And I'm going to deal with it by multiplying by the number 1. It's a special number 1 that I'm going to multiply by. The number 1 that I'm going to multiply by is selected because of this thing's exponent. I can see this y is being raised to the negative second power. And if I want a negative exponent to go away, I'm going to multiply by the same base, but the opposite exponent. So I'm going to take this y to the negative second, and I'm going to multiply it by y to the positive second. And in order to keep this expression equal to itself, I'm going to multiply by y to the second up top as well. So you can see this expression is not changing its value because all I'm doing is multiplying by the number 1. And the reason why I picked this particular number 1 is because I want this negative exponent to go away. Now, when I multiply y to the negative second times y to the positive second, that's y to the 0 power, which means I have no factors of y. Having no factors of y doesn't mean I have the number 0. It just means I have the number 1. So I've got no factors of y, so what I'm left with is just the number 1 in the denominator. So I can write as an almost final step, this is 3x squared y squared over 1, or just simply 3x squared y squared. 3x squared y squared. All right, so that's it for page 1. Let's move along to page number 2. Down in page 2, we're asked to solve an equation below, solve each equation below, and there's just 2 of them. And it says include a check for your solution. So this first equation is a nice example of this idea we've talked about of fraction busters. I can get rid of the fractions here by multiplying by an appropriate number that would destroy all these fractions, just wipe them out. And the reason why I can do that is if I have an equation, I can multiply both sides of it by the same value, and I don't change the solutions to that equation. I just tweak the equation. So I know that the number 8 contains a factor of 2 in it. So if you're looking at some numbers, one thing to try is just go ahead and multiply both sides by the largest value. So I'm going to multiply by the number 8. Not 8 over 8, because that would be the number 1. I'm going to multiply both sides by 8. And when I do that, I'm going to have to place a factor of 8 here, here, and here. So if I'm going to go ahead and write this below, but where those green dots are, every single term on the left and right-hand side has to get a new factor of 8. So this is going to become 8x over 2 equals 8 times 3 over 2 plus 8x over 8. Now, the reason why that's advantageous is if I look at each one of these terms, this first term right here, 8x over 2, is just the same thing as 4x, which is just sweet, the fact that that no longer has a fraction. It's going to equal 8 divided by 2 is also 4, and then 4 times 3 would be 12. This is going to become 12, right? 8 times 3 over 2 is 12. And then finally, there's going to be a single plus the number x, because 8 over 8 is 1. All right, so let's bring this up here and finish. What we're going to do now to finish this is I'm going to go ahead and subtract x from both sides. When I do that, I'm going to get 3x on the left-hand side, and then the right-hand side is going to become just the number 12 because I'm subtracting an x from each side. And then finally, I'm going to divide both sides by 3, and I get that x is 4. That's what I get when I divide both sides by 3. Now, the problem did say include a check for your solution. So real quickly, what that means is I just need to confirm that the left and the right-hand side are the same number. I'm not sure what that is yet, but actually this is really easy to do, even without the calculator. But I'm going to go ahead and use it anyway. So I'm going to take the number 4 and store that as x. And I'm now going to go ahead and type the left-hand side, which is x over 2. I know what you're saying. 4 over 2 is 2, and I see that. And then the other side is going to be 3/2. Okay, 3/2. And then I'm going to add 2 3/2 plus x over 8. X over 8. And when I do that, you can see in both cases, I got 2. The left-hand side became 2, right? And the right-hand side became 2. 2 is equal to 2. This is confirmation. This is a check. The left-hand side became 2 with my value of x. The right-hand side became 2. That's a solution to this equation. All right, moving along to the next equation, you can see I've got these decimals here. I could proceed to solve these with the decimals, but the decimals are a bit problematic, and I don't need to deal with them, because if I multiplied both sides of that equation by the number 100, the decimals would cease to exist, right? 28 or 0.28 times 100 is just 28. So I'm going to go ahead and very intentionally multiply both sides of this by 100. And I picked that value because you can see I've got tenths, hundredths, right? All these tenths, hundredths, tenths, hundreds. So they're going to make the decimals go away. over on the left-hand side, 0.07 times 100 is just going to become 7x minus 0.07 times 100 is going to be just 7, and then that's going to equal 28 times 100 is 28. Now, I know that step is not necessary, but I think what we have now is much easier to look at than what we started with. The next thing I'm going to do is go ahead and add a 7 to each side of this equation. So if I've got my number 28 and I increase that by 7, I'm looking at 35. So this becomes 7x is 35. Adding 7 to each side, sorry about that. Adding 7 to each side produces this. And then finally, I'm going to divide both sides by 7. When I take that left-hand side and divide it by 7, I get the number, I get x, right? This side is just going to become x when I divide it by 7. And the other side is going to become the number 5. So x is 5 is my solution. And again, you're instructed to produce a check to make sure both sides, in this case, because this already equals 0.28, both sides should equal 0.28. So I just should confirm that this is 0.28. Now, I don't have to do the whole store x thing. I'll just do a quick check here. I'm just going to take 0.07 times 5 and then subtract from that 0.07. And when I do it, you can see I get 0.28. So clearly x is 5 is the value that makes both sides of this equal to 0.28. So there is the required check, confirmation that both sides become the same. In question 4, we're given an expression. We're not given anything about the situation that this expression models. We're just asked to evaluate this expression with some given inputs. We're given an input for x, for y, and for z, and we're just going to plug those in. So I'm going to write right below this, here's going to be a place for my value y, and I'm going to square that, minus, here's a place for my x, and I'm not squaring that, and then plus 3 times some parentheses. Here is a space for my x, plus 6 times here is a space for my y. So I'm going to go ahead and take each of those values, right? I've got this y. No, that's a z, and z is going to go here, right? Because that's where z was. X appeared in 2 places, right? X is -3, and x occurred both here and here in the original problem. And then y only occurred once right here. So I'm going to be placing the value y in. So for y, we've got a number of -2. So -2 is going to land there for y. For x, we're going to place a -3 inside. Over here, we're going to place a -3 inside. And then for z, we're going to place the number 1/3. So if I take a look at this, -2 squared is 4. And then I'm going to subtract a -3, which means I'm adding 3. And then I'm going to have plus 3 times some quantity. Inside of there is a -3, but to that I'm going to be adding 6 times 1/3, I'm going to be adding the number 2. So that means inside the parentheses there, -3 plus 2 is going to be -1. So what I think I'm looking at here is 4 plus 3, and then a 3 times plus 3 times a -1, which means I'm just subtracting 3. So that means that the final simplified version should be just the number 4. Now, I don't know why I feel suspicious of this, so I'm going to check this on my calculator as well. So I'm going to just open parentheses. I'm going to take the -2 value, and I'm going to go ahead and square that. And then I'm going to subtract, and this calculator doesn't need these, but I'll do it anyways. So subtract a -3, and then I'm going to add 3 times, and inside I've got a -3 plus 6 times 1/3. And I'm going to close off those parentheses, and I get a number 4. All right, so we were correct. Oh, I just did all that on a calculator screen, and you didn't see it, but I checked it. It worked. It was nice. All right, next, write these numbers using scientific notation. So the first one is given in scientific notation. No, it's given in standard notation. We have to write it in scientific notation. The other one's given in scientific notation, and we have to write it in standard notation. So in scientific notation, we always just have a leading digit, right? A number that's bigger than 0 No, it has to be bigger than 1, but less than 10. So it's going to be 4.1, right? So my decimal has to be right there, 4.1. But in order for 4.1 to equal 410,000, I need to multiply that by a bunch of tens, right? And you can see this on a calculator, right? How many tens do you need to multiply it by? You can count them, but I can count them right here too, because the beautiful thing about multiplying by 10 is it's easy to do because you're just moving decimal points. But to demonstrate this, I'm going to go ahead and throw the 4.1 on the screen. So here's my 4.1. So I'm placing the 4.1 on the calculator stack, and then I'm just going to multiply by 10. So I'm going to multiply by 10. How many times? 1, 2, 3, 4, 5. And you can see right there, if I multiply by 10 5 times, that becomes 410,000. The nice thing about scientific notation is we don't have to write times 10 times 10 times 10, right? We just say, hey, multiply by 10 5 times. So that's why we do that. Now, I know that at some point you've seen a science teacher or someone show you that what we're doing here is this decimal place is moving from where we placed it, right? We placed it right there, but it has to move this way 1, 2, 3, 4, 5 times to get to where it was originally. So we've taken 4.1 and we've grown that back up to 410,000 by multiplying by 10 copies of the number 10. Now, this next one, right, we've got 1.4, and we're asked to write it in standard notation. Now, we'll notice that this is not factors of 10. These we're multiplying by 1/10, right? Remember, when I see 10 to the first power, that's just 10. Boom. But when I say 10 to the negative 1 power, that's 1/10, right? So this means I'm dividing by the number 10. So I've got the number 1.4, right? That's where this is starting. But I have to divide by 10 how many times? I got to divide by 10 1, 2, 3 times. And I can see this happen on my calculator. I'll just stack the number. I'll put 1.4 on the stack. There it is. And I'm just going to say, oh, let's go ahead and divide that by the number 10 3 times, because it was to the negative third. 1, 2, 3. And there we go. So if you look at it, all I'm doing is moving my decimal place 3 places this way. So my answer then is 0.0014, 0.0014. And again, if I take a look, right, this is where the decimal was in the original problem, and I'm expanding that. I'm going into standard notation by undoing this, getting rid of this, and just doing those operations, and it had to move 1, 2, 3 places. So this is this number in standard notation. All right, find the equation of a line through 2 points. So we're given 2 points, and we're asked to find the equation of a line that passes through those 2 points. One of the things you can do to kind of clearly organize your work is identify your 2 points. I could say, hey, here is the x value from my first point. Here's the y value from my first point. Here's the x value from my second point. And here's the y value from my second point. And then remind ourselves that slope, which we need, right? If I'm asked to write the equation of a line, I need 2 parameters. I need my slope parameter and my y-intercept parameter. My slope parameter, right, we use the variable m for it, is equal to the change in the y's divided by the change in the x. So I'm going to write, you can write y2 minus y1 over the change in the x's, x2 minus x1. So that's just a reminder, which is equal to, in this case, I'm going to look at -1 minus 3. And then down in my denominator, I have 9 minus a -3. So what am I looking at here? In the numerator, it looks like I've got the number -4. And in my denominator, it looks like I've got 9 plus 3, which is 12. So my slope, I'm pretty sure this reduces, it reduces to -1/3. So that's great that I organized it and did that, but I also want to remind you, if you're struggling with arithmetic, right, keep working on that, but while you're working on that, don't tell yourself you can't do the algebra. You can do the algebra. It's the easy part. So I'm just going to use this calculator to do the arithmetic for me. So I've got the -1 minus 3, and in the denominator, I'm just going to type 9 minus the number -3. And you can see it reduces to -1/3. So I know my slope parameter. The slope parameter is m. M is -1/3. What I need to do now is I need to figure out my y-intercept parameter, b. So remember, in the equation of a line, right, y equals mx plus b. There are two variables. Our variables are x and y, and our parameters, the things that control the line and tell the line what kind of line it's supposed to be, are m and b. And in the case that I know my slope, right? I know this value, but I also know some x and y values, right? So if you look closely, right, I know an x value and a y value, and I'm going to use this x value and y value in order to figure out what my y-intercept is. So in for y, I'm going to place the number 3 because y from the point I'm using is +3. In for my slope was -1/3. And then in for x, I'm placing the number -3. And then plus b. So you can see here, all I've got are numbers now, except for b, the thing I'm trying to find, my y-intercept parameter. -1/3 times -3 is +1. So this equation is 3 is equal to 1 plus b. And then if I take away 1 from each side, this equation tells me that 2 is the value of b. So brilliantly, we've got both of our parameters. We know our slope parameter and we know our y-intercept parameter. So we can write the equation of this line. The equation of this line is y is equal to -1/3 x plus the number 2. All right, there we go. We got it. But hey, let's test and see if we're correct. Because if we're correct, two things have to be true. These 2 points that we have to produce the right value. So a quick way to check if we're looking at the correct equation is to use our table function. So in our table function, I'm going to type our equation, -1/3, and I'm multiplying that by x, and then I'm adding to that the number 2, enter. I'm going to create a table that starts at 1 and steps by 1, and it's going to automatically generate it. So boom, here we go. So the two things I care about are these points on this table. In other words, if I go to -3 for x, does it say 9? So let's go up to -3 for x. No, I'm sorry. If I go to -3 for x, where am I at? Where's my pen? If I go to -3 for x, does it say 3? And the answer is yes. It clearly says 3. So this point is happy. It's satisfied. This point satisfies this equation. That means this point is on this line. This point is a member of this line. The other point that has to be true is when I go way down to when x is the number 9, 2, 3, 4, 5, 6, 7, it has to be the case that I get -1. And you can see it clearly happens, right? When x is 9 for that equation, it produces a value of 1. So both of these points, right, are on the line. That means I clearly have the equation of the line. All right, let's move down to question 7. It says, find the equation of a line that is parallel to y is equal to 2/5 x plus 15. So one of the things we remember is that parallel and perpendicular, right? And just as a side note here, we'll just go ahead and write this down. If we've got parallel lines, they will always have the same slope same value of m. And just as a note, perpendicular lines, this is the symbol we use for perpendicular. These are lines that meet at right angles. They have slopes that follow this pattern, right? If one of them is a over b, the other one has to be the opposite of that and the reciprocal of that. So it's always going to be whatever the sign is, we're going to go to the opposite side. And so if it's positive, it's going to become negative and vice versa. And it's the reciprocal, we're just going to flip our numerator and denominator. So perpendicular lines are formed that way. So for example, if I've got a line that has a slope of -3/4, the perpendicular slope would be positive 4/3. And if I was to graph those, it would be very clear to me quickly that they're making if they're making a perfect right angle. So I know my slope parameter because they give me an equation of a line. They give me this line. This line is given. And from this line, I can see what its slope is, right? Its value of m is 2/5. So, and because we're talking about parallel lines, the equation I'm going to be writing is going to have the exact same value of m because they're parallel to each other. They're parallel lines. So what I need to find now is my y-intercept. I know my slope parameter because the lines are parallel, but what's my y-intercept parameter? And I'm going to do the same thing I did above. I'm writing y equals mx plus b. And in that, I'm going to place the x value and the y value from the point I'm given that my equation has to pass through. It has to go through that point. So I'm going to say, hey, y is the number 12. My slope, my known slope is 2/5. And my x value is 10. And then I've got plus b. So I need to evaluate that and figure out what b is. I think I'm not a fan of arithmetic. I can do arithmetic, but what I really struggle with is seeing students, some of you struggle with arithmetic, and I just want you to know that's okay. Just use this tool, and the more you use this, you're going to find that arithmetic kind of just starts to click, and you'll become an arithmetic master. So I've got 2/5, and I'm multiplying it by 10. So this equation simplifies to 12 is 4 plus b. And then I'm just going to subtract 4 from both sides. 12 minus 4 is 8. And the other side is going to become b. So I know both of my parameters now, right? I know the information required to make the equation of the line. And the equation of the line is this. Y is 2/5 times x plus the number 8. So question, does this line meet the requirements for the line I was given? First of all, in terms of the slope, yes, I was given a line that had a slope of 2/5, and I needed to be parallel to that line. So because I have an equation with a slope of 2/5, I know that my line and the given line are going to be parallel to each other. But the other thing that has to be true is that my line has to pass through the point 10, 12. Meaning, if I give this line a value x is 10, right, it has to give me back a y value of 12. And without typing the table value in, I'm just going to do a quick check of that. Let's look at 2/5 times the number 2/5 times the number 10. If I give it 10 times 10, and then to that, I'm going to add 8 plus 8. So when I put, what I'm doing right now, you can see I'm just putting in this x value. I just put x is 10 into here, and I type the entire expression. So I'm looking at 2/5 x plus 8. And when I type that, I get exactly the number, ta-da, 12. So for sure, this point is on the line that we produce. So this line has both properties it needed. It's parallel to this line, and it will definitely go through that point. So that is our solution. All right, next. It says graph the following rules on one set of axes. I don't know if I spelled that right. Axes. I think that's wrong. Label each line with its equation, the y-intercept, and a slope triangle, any slope triangle. First equation right there, I'll use the color green. Let me circle this. Maybe this will work. Maybe it won't. It has a y-intercept down at -4. So if I'm plotting down, I go 1, 2, 3, 4. This is the y-intercept at that point. And it has a slope pattern of down 1 over 2. So I go down 1 over 2, down 1 over 2, down 1 over 2. And it's just nice to extend that out as far as you can. I think I can grab, no, that last one was wrong. I went down 2 over 2. I'm supposed to go down 1 over 2. So I'd land right there. If I grab the line tool, I think I can draw a line quickly here. That's good enough. And then I'll go ahead and just draw arrows on both sides, meaning it continues indefinitely. I'm going to draw a slope triangle by putting a little down 1 over 2, right? Negative 1, 2. There's a slope triangle for it. The y-intercept is at -4, right? I'll just point out this is the number -4. And the other thing it says is write the equation of the line. So I'm going to write right here, this is y is equal to -1/2 x minus 4 from it. Next thing we have is b, and for b, I'll use a blue, I guess. For b, we've got this equation, y is equal to 2x plus 2. So I'm going to pop up to +2 and put our first point. And then I have a slope of pattern of go up 2 over 1, right? So up 2 over 1, up 2, up 2, and up 2. All right. So I'm going to go ahead and grab, I hope, a straight line tool ruler and just draw that line. And you can see there we go. And that should be this second line. It's got the correct slope and the correct y-intercept. I'll draw a slope triangle on it right here. Up 2 over 1. There's a slope triangle. I can see the rise and the run of that. And the other thing it says is show me the y-intercept, right? So the y-intercept is right here. It's at +2. And write the equation of that line. That line has the equation y is equal to 2x plus 2. So those first two are pretty straightforward because they were written in slope-intercept form, and I could easily see both parameters. I could see the slope parameter and the y-intercept parameter, and then go from there. This third one is a little bit problematic because it is not in the form. It's not in the form y equals mx plus b. But that's okay because we can rewrite it so that it's in that format. The hallmark here is notice that the y is by itself. So what I need to do is I need to get this y alone. And in order to get that y alone, I'm first going to get 4y alone. So if my job is to get 4y alone, I'm going to subtract 3x from both sides. So this equation is going to become 4y. What did I just do? I just took away 3x from that left-hand side. Is going to equal, this is me taking away 3x from the right-hand side, and then plus 16. So both sides, 3x was removed from both of the sides. And then next, I'm going to undo this multiplication by 4 by dividing both sides by 4. When I divide by 4, this is going to become y. And when I divide the other side by 4, you can see there's two separate terms, and I have to divide each of the terms by this value. So I'm going to divide both of the terms by 4. So it's going to be 3 over 4x. And then plus 16 divided by 4 is 4. So these equations are the same equations, right? They'll have all the same x, y values at work. The beauty of this second format is I can now see my two parameters. I can see my slope parameter and I can see my y-intercept parameter. So I'm ready to go ahead and graph this line. Let's go back to our graph. We're starting here at the value of, is it +4, really? Yeah, it's at +4. So way up here at +4 is where this is going to begin. And then this thing had a slope triangle of -3/4, right? Down 3 over 4. So from here, I'm going to go down 1, 2, 3 over 1, 2, 3, and 4. There we go. Then I'm going to go down 1, 2, 3 over 1, 2, 3, and 4. Okay. Let me go the other way a little bit. I can also go up 3, 1, 2, 3, and then backwards 4, 1, 2, 3, and 4. You see this is the same line. Up 3 and backwards 1, 2, 3, and 4. There we go. All right, so we've got this line. Let's go ahead and grab our line tool and draw it. Okay. There we go. And I'm going to extend the line in both directions. I'm going to include the requisite slope triangle of down 3 over 4. I can see it right there. I'm going to point out the y-intercept is at +4, and it's right there. And I'll write the equation of this line. It's y is equal to, oops, it's a little off your screen. Y is equal to negative 3/4 times x, and then plus the number 4. All right, so there we go. We've just reviewed drawing some lines. We've drawn those 3 lines. All right, let's go to question number 9. Question 9 says we're going to start with a triangle, and then we're going to be asked to do 2 things. We're going to be asked to take that triangle and then rotate it, and then take the rotated triangle, and this is tough, and then we're going to translate that using this translation rule. These are our rigid transformations. So we're going to have to rotate 90 degrees. Oh, remember slopes, opposite reciprocals. Opposite reciprocals are going to help us with that. And then after we translate it, we're going to take that and we're going to do one more thing to that. It says we're going to reflect it across the line. X is equal to -2. Ooh, that looks exciting. X is -2. And we're going to produce a final triangle. So when we're done, we should have our original triangle and then 1, 2, 3 more triangles here. So that's a lot of things. So let's go ahead and begin with the first triangle. The first triangle is found by plotting these values. I don't think I need the on-screen calculator right now. So let's go ahead and begin by plotting these points. Just by way of review, an ordered pair contains an x value and a y value. All of them do. I don't know why I wrote that right over the number 2 where you can't even see it. So we've got an x and a y. And here is our x value. That's our x-axis, rather, and this is our y-axis. And we're going to go ahead and plot each of these points. So the first point is x is 1, y is 2. This is the point A. Our next point is x is 5, and y is the number 1, 2, 3, 4. So this is the point 5, 4. This is B. And then x is 6, and y is 1 is our last point, and that's the point C. Now, probably I'm starting with the most difficult transformation. I'm asked to rotate this thing 90 degrees. Does it say clockwise or counterclockwise? Counterclockwise, 90 degrees against the clock from here. So it's going to be a bit tough. Let's see. But we can look at each one of these points individually, and I think we can figure this out. So this point A, if I draw a line from A back to the origin, right, that line has a slope of up 2 over 1. Well, instead of going up 2 over 1, I need to have a slope of -2, -1/2. So I know because I'm going this direction, this point is actually going to be over here. And if I put this point right here, take a look at this. This point now back to here, that has a slope of -1/2. Well, if the slopes are -1/2 and 2, I know that this is 90 degrees. So I just subjected point A to this 90-degree rotation, and I identified the location of point A. So I'm going to go ahead and erase those things, and I'm going to go ahead and place this point A right here. But it's no longer called point A. This is now A prime because it was subjected to a transformation. So we've moved A. Yay. Now we got to move point B. I'm going to try and do the same thing again. The line for point B to move is right here. Now that line has a slope of up 4 over 5, right? This line has a slope of 4/5. And in order to make a right angle, I need a slope of -5 over 4. Well, again, I know I'm going this direction, right? I'm going counterclockwise. So thinking of where I'm at, what I'm going to do is I'm actually going to go up 5, 1, 2, 3, 4, 5, and then backwards 4, 1, 2, 3, and 4. So this is the location right here. If I look at it, it's pretty convincing, right? Because these slopes are opposite reciprocals, it looks like that would be a 90-degree rotation in the counterclockwise direction. So I think we just found the location of our next point. This next point was B. It was B, but now it's going to be known as B prime. So we have B prime. We got to do one more. We got to do C. And unfortunately, I think I was not brilliant when I created this question because I think I run out of room for it. Yeah, I do run out of room for it. So the last one is C. You can see C from the origin to C, there's a slope of 1/6, up 1 over 6, up 1 over 6, up 1 over 6. Well, in order to be 90 degrees from that, I need to go up 6 and, well, okay, this is up 1 over 6 and it's positive. To make a right angle, I'm going to need to go, I'm going to need to go, I'm going up 1 over 6. I'm going to need to go, this is the slope I need, right? I need a slope of -1/6. So what I'm going to do is, my gosh, I know that it has to go counterclockwise, so it has to go back here. So I think I got to go, yuck, because it's off my screen, or it's off of my grid anyways. I have to go, I'm going to go up 6, 1, 2, 3, 4, 5, and then up here is like 6. But then I have to go backwards 1. Oops, right here. So this point, which is unfortunately off the graph, right, that's the slope that I need to make that right angle. So I've got that right angle transformation there. So what? So what is, I'm going to go ahead now and plot that point. I'm using green for this one, I guess. And this is now C prime. All right, so I have my original triangle. My original triangle is right here, right? I've got A, B, and C. And this triangle was subjected to a 90-degree rotation about the origin. And after that rotation occurred, we get this new triangle that's like, whoops, that's not a triangle. That's not a straight line. What? Erase? That's not a straight line. This is better. This is better. And this is better. So we've got this new triangle. So you can see step 1 complete. We did a 90-degree rotation about the origin. The next thing that we need to do is, the last two are way easier, right? The next one is we just need to translate this using the following rule. The x values, so when I look at this rule, this is a transformation rule, and it says that for every single point on the triangle that I just made, the x values are all going to be increased by 5, and the y values are going to be decreased by 6. So I like this one because I just have to count, and I don't have to think about those slopes and right angles. So, by the way, you guys have used patty paper in class. I have that patty paper in a back box, so feel free to use that if that's easier for you. There's other ways to do that problem that we just did. But from here, x's are going to increase by 5, y's are going to go down by 6. So I'm going to do A first, and I'm just going to go over 1, 2, 3, 4, 5, and then down 6. 1, 2, 3, 4, 5, 6. So this is my second version of A prime, and it's going to live there. Same thing for B. I got to increase its x by 5. 1, 2, 3, 4, 5, and then down by 6. 1, 2, 3, 4, 5, 6. This is where B goes, or B now double prime. And then for C, I'm going to increase by 5 the x values. 1, 2, 3, 4, 5, and I'm going to go down by 6. 1, 2, 3, 4, 5, and 6. This is my value of C prime. All right, let's go ahead and draw that triangle in. I've got this line segment, I've got this line segment, and I got this line segment. So there is this triangle. Very nice, right? Because all I'm doing here is just subjecting it to this nice translation. Easy to do, no rotation involved. I like this much better than the previous one. And you can see this rule again is, what did I do to every single x value that I started with? Right, each and every x value was increased by 5. So the new x's are 5 bigger than they were before. And each y value was decreased by 6. So it moved down 6 and it moved over to the right 5. All right, the last thing I'm asked to do is to reflect this triangle across the line x equals -2 to produce a final triangle. X equals -2 is a little tricky, right? Anytime I want to draw a vertical line, it has to take this format, X is -2. And if you're confused by that, I just say, hey, just start plotting some points where that's true, right? Hey, here, right here, X is -2. Hey, right here, X is -2. X is Y's are changing, but on this line that goes straight up and down, the X's are all -2. So what we're being asked to do is to reflect this shape across this line. So we're going to take our final triangle that's in blue, and we're going to reflect it across that line. And the reflection's easy too, right? Because when I reflect across a line, the distance from this point to where it goes to has to be the same. So this is 1, 2, 3. So this is going to be 1, 2, 3. So this is going to be where B triple prime goes. And for A, this is what? 1, 2, 3, 4, 5. I'm going to go 1, 2, 3, 4, 5. This right here is where A triple prime goes. And the last one is C, which is what? 1, 2, 3, 4, 5, 6. I have to go 1, 2, 3, 4, 5, 6. This is where C triple prime goes. So let's go ahead and draw this final triangle there, there, and of course in the back we always have a box of rulers in the classroom. So when you're doing this on a test, please grab a ruler and make straight lines. All right, and that is the final look at what happens here. So definitely the first one there is the most challenging. To be honest, I don't know that I'm going to give you a rotation like that, but with patty paper, it's very doable. But you can see the translation is pretty straightforward, right? This is not bad. And the reflection across a line, like X is -2, is not bad either. Right, moving on to the final page of this practice test. The first question here is, what is the perimeter of this shape that was created with algebra tiles? So the perimeter. And if I come in and review here, this first tile that I'm starting with is an X tile, and its dimensions are 1 times X, right? So it's 1 tall and X wide. So that's good because I know that this, right, is 1 unit and that this is 1 unit. The tile above it is an X squared tile, and I know that this has to be X units long. And because it's an X squared tile, this has to be X units long. The neighboring tile is also an X squared unit. This has to be X long. What I'm going to be doing is starting here and walking this way around this entire shape. And as I walk around it, what I want to be getting is each one of those lengths and then adding those up to get the perimeter. If I continue, this is X units long. This is X units long. As I go down, this is just from here to here is just 1 unit. This is X units. Now, there's 2 bits that are a little bit tricky, and I'm going to highlight one of them right here in green. This right here, right? I can't assume that that's 1 long. I don't know. That's not what I meant to say. I can't assume that from here, from this dot to here, I don't know that that's 1, right? But what it is it's an X and then 2 is taken away from it, right? You can see inside of it, it's X wide, but then there is a 1 and a 2 that are subtracted from it. So this piece right here is X minus 2. And if I continue on with the red, this is a 1, this is a 1, this is a 1. Then I've got another bit that's a little bit tricky, and it's right here. From this point to this point is a little bit, it's actually just the same thing as above, right? This is a little bit tricky. What is it? Well, this whole piece is X, but then there's a 1 and there's a 1. So this is also equal to X minus 2. Continuing on around, this next one is X long. This is a 1, and this is a 1, and then down here is an X. So those are all the pieces. Now I just got to put them together. So I do see that there's two -2s here, right? And then these are X's, and they're positive. So if I just go through and count all my positive X's, I think that's not a bad strategy. I'm just going to circle the ones in reds that I've counted. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 x's. So I think part of my perimeter is 10 x's. And now I'm going to go around and I got to count up all the ones I have. And I have to remember, I might write this down right now. There's a -4 that I need to take care of because I've got a -2 here and a -2 here. So that's a -4. Now let's just count the positive ones going around. So I've got a 1, 2, going this way, 3, 4, 5, 6, 7, and 8. So I've got a +8. So if I simplify that, I believe the correct perimeter is I've got 10x and then plus just the number 4. So that is the perimeter of that shape. That's me walking around it. The other thing that we've worked on quite a bit is finding the area of algebra tile, or using algebra tiles to do multiplication problems. So this is not a generic area model. This is a very explicit area model using algebra tiles. And if I look at the height of it, this is 2x's plus 1 tall, and the width of this is an x plus 1, 2, 3. So when I multiply length times width, I get area, right, for a rectangle. What I'm multiplying here is I've got a 2x plus 1, and I'm multiplying that by x plus 3. And when I do that multiplication, because this is an explicit model, what do I get? Well, I get 2x squareds, right? I get 2x squareds. I get 1, 2, 3, 4, 5, 6, 7 x's plus 7 x's, and I get 3 1s plus 3. So this, right, is what's represented by this problem. This is the product of 2x plus 1 times x plus 3 is equal to 2x squared plus 7x plus 3. Now, of course, we do not draw area models like this. What we do is we look at, hey, if I ask you to do this multiplication problem, right, we've been building generic area models where it's a 2 by 2 grid, and I'm multiplying 2 things times 2 things, and I write, hey, this is 2x, and this is x, this is 1, and this is 3. So you can see exactly where the 2x plus 1 is shown here, 2x plus 1, and then I've got an x plus 3, and that's what this is. It's an x plus 3 more. And when I do that, I can get the area of each of those individual little rectangles. This area of this one is 2 times x squared, right? It's 2 times x times another x, 2x squared. Right below that is x. Up above here is 6x. What's that? That's 2x times 3. And then below that is 3. And you can see that 2 of these are like terms. And because these are like terms, they can be combined. And when I combine them, I do get the 7x. So you can see everything's here. You can see that I've got a 2x squared, which I found. I've got 7x, which is here. And I've got the 3, which is right here. All right, finally, it says use the distributive property. This is the last question. Use the distributive property to find each product. Use a generic area model to organize your work if needed. All right, so I don't think I need a generic area model for this problem, right? This is the simplest form of the distributive property. I'm multiplying this side by 3, so 3 has to be distributed to each of 2 terms. Terms are those things that are separated by plus or minus, so I've got 2 terms here. This is going to be the same as 3 times x, or 3x, plus 3 times 6 plus 18. So when I multiply that 3 times the quantity of x plus 6, I get 3x plus 18. And then last problem. This one's a 2 by 3 area model if I want to do it with an area model, and I do. So I'm going to go ahead and sketch an area model that's going to be 2 tall and 3 wide. I'll divide this into 2 pieces, and I'm going to divide the width into 3 sections, 1, 2, and then 3. For the up and down, I'm going to go ahead and write, well, this is a y plus an x, and of course that is modeling this part of it. So I've got y plus x, y and a positive x, and then across the top I'm going to have an x, and then plus a 3y, and then a minus 4. So, and you can see that's exactly what I had here. I had an x plus a 3y and then a minus 4, x plus 3y minus 4. Again, we multiply to get the areas. So if I find the area of each piece, this first one is going to be y times x. And you can write that any way you want, but I'm going to write it as, I don't know why xy, but I'm just multiplying y times x. Below that, this rectangle has a height of x and a width of x, so this is an x squared. Up in the middle, I've got a y times 3y, and 3y times another y is 3yy, or 3y squared. Below that, I've got a 3y times an x, and I'm gonna write that as 3xy. 3xy, 3yx is the same. I know why. And then in the upper column in the last, upper row in the last column, I've got a negative 4y, and below that, I've got a negative 4 times x. So not a lot of these are like terms. However, there are two that are like terms. These are both xy's, right? Or yx's. And because they're the same, I can combine those. So my final answer is going to be that this original problem is equal to the following. I'm going to write that it's got an x squared, check. It's got a 3y squared, check. It's got 1, 2, 3, and then 4. It has plus 4 of these things called xy's, check. Then it's got a minus 4x, minus 4x, and then it's got a minus 4. Nope, don't forget the x. It's got a minus 4x, erase that. It's got a minus 4x, and then it's got a minus 4y. So when I multiply x plus y times x plus 3y minus 4 together, right, what do I get? I get the following. I get x squared plus 3y squared plus 4xy minus 4x minus 4y. All right, use this as you will. Look at just certain parts, chop it up, clip it down, play me at 3x speed, play me at half speed. Just do whatever you need to do to kind of digest this information, think about this more deeply, and figure out what's going on. I wish you well, and I'll talk to you soon.